Hello students, so in this lecture we will be discussing about density of states, and we will be plotting the density of states of related to different confinements through MATLAB programming. Now first we need to understand what is density of state is. So the density of states can be defined as the number of quantum states available per unit energy in a system. Now, if we take a system, the very basic system of x, y, and z dimensions, and would like to find out the density of states of the free electrons in that system. Now, to do that, first we need to know what is the relationship between the energy and the wave vector or the momentum of the system. So this k is basically the wave vector. So P is equal to h cross k de Broglie's hypothesis. And so if we allow this value to be included in the energy versus k relationship, that is, we know that E is equal to P square by 2m, the kinetic energy. So substituting this value in this equation, we get this expression. The only thing is that the m here is not the rest mass, it is the effective mass of the system, effective mass of the charged particle. That means the mass which gets affected by the internal arrangements of atoms in the 3D system. Okay, so this is the expression. Now, as we have previously said that it is the number of quantum states available per unit energy in the system, and so to find out we need to know the total number of states up to this energy E, and this is actually proportional to a volume of a sphere in the k space. So we are now converting our focus from real space to k space, and the number of states per unit energy, that is the density of states, is actually the number is proportional to the volume of the sphere in the k space. The volume of the k space, if having a length dimension k, automatically the volume will be k cube. And if we again express this in terms of energy, it will be 3 by 2, because energy is related to k in a parabolic manner. So that's why we actually get the valence band and conduction band diagram. So we have noticed they are basically based upon this EK diagram. So we get a parabolic curve. The difference in curvature is mainly due to the fact that the electronic effective mass of electron is higher than the effective mass of a hole. That's why there is higher curvature in the case of electron, whereas lower curvature in the case of valence band. So this corresponds to the valence band, basically the holes, and this is the conduction band, basically represents that of electrons. Okay, now if we Ne, that is the number of states up to energy E, we expressed as in terms of k, then when expressed in terms of E gives us this value. So if we now differentiate this with respect to E, we get that we find that the density of states, which is GE is d by d of n is proportional to root over E. That means it has got a parabolic nature. Okay, now this is the parabolic in nature. That means plotting the density of states versus E, we get this, according to this relationship, we get the following plot. Okay, now before going into the details or before going into the programming, uh, we let us first recap what we have learned in previously in deriving the expression of wave function and energy for a particle in a box model. Now this particle in a box model is very important because in for the case of any study related to nano dimensions, say nanoelectronics, nanomagnetism, nanophotonics. Because when we are going to this nano regime, we are basically confining the electrons with a certain potential. And the potential is where the confinement dimension, reduction of the confinement dimension takes place. Now, particle in a box model, we are assuming that there is a box with certain dimension, Lx, Ly, and Lz, and there is an electron inside which is free. This is the Schrodinger's equation, and this is the boundary condition. And so this is a well-known Schrodinger's equation, which solution is this one, 2L, root 2L sin n pi x by L, and the energy is for one dimension expressed in this fashion, that is a square by 2m divided by nx by lx. This lx is the dimension, and nx is related to the number of states, quantum states available. Now again, if we consider the energy versus the P or the K relationship, by relating these two equations, we can derive that the momentum in the three dimensions, the Lx, x, y, and z, is can again be expressed in terms of this number and L. So Px can be expressed as h n x by Lx, correspondingly Py and Pk or Pz. Now, for a very small volume, that means for a microscopic volume, it is in the denominator. It is Lx. The dimensions are in the denominator. So, for a macroscopic volume, this Lx, Ny, and Li are large. So, the momentums are very closely spaced. That means if nx, taking the values of integral values of nx, say nx 1, 2, 3, even if we take nx to say a certain number of a certain higher number, then also since lx is in the denominator and we are dealing with a microscopic system, the microscopic system momentum components are very closely spaced. And if in this situation, if there is a small change in momentum, it maybe allow its states in each direction. And each of the x, y, and z direction, there may be many number of allowed states. By allowed states, I mean delta nx, delta ny, and delta nz. These are the allowed states. Okay. Now we move a little further in the study. Now, if delta nx is a number of states between, if we take one dimension, is a number of states between px and px plus dpx, then we can express delta nx as lh by h into dpx, and the same goes for the other dimension. So, the total number of momentum components to lie between Px and Px and Dx is the product of these three number of states. And so if we do the product, we come up with this expression, and we again represent this Lx, Ly and Lz. This is basically the volume of the particle in the box we started with. This is Lx and Lz, and this is the volume, and same has been shown here. So it's volume of the particle, volume of the box into this quantity HQ, which HQ is also a volume, but this is a volume of phase space. A phase space is a space which consists of the three components of the real space and the three components of momentum space. So its dimension is 6. So the number of states can be found out if we divide the real volume by the phase space volume of H cube. This gives us the number of states. This is what H cube. So number of quantum states obtained by dividing the phase space into cells, each of having volume H cube. Now this situation is somewhat having a sphere, as previously told, of radius say P, and there is small change in P stands for the momentum. There is small P or K, whatever it means, the same P is equal to H cross K. So if there is a small change in P, as previously told, there will be a lot of states available. So a change in P, that is dP again, can be expressed in terms of energy by this expression. If we differentiate this equation, we get this following value of dB, and the density of states in terms of momentum will be again equal to the area, 4 pi r square into dB. So volume of this momentum space. The volume of this momentum space is surface area, that is 4 pi p square into the change that has taken place. So this is the volume, and this again, if we express the P in terms of E, which can be very easily done, we ultimately obtain the density of states for a free electron in a 3D system. Now next step is to write the codes of the following phenomena in MATLAB. So MATLAB is comparatively easier or less complicated compared to other programming languages. So in a MATLAB, let me just give you some basic idea that a percentage sign is used when you are doing some comment. Okay, so like here it has been used to give the heading of the program. Then there's a command called CLC, which clears the stream, and clears all previous data. Then apart from that, so what we will do in through this MATLAB, we will try to generate the expression. We will try to generate the density of states versus energy plot. Okay, so first we need to define the constants, which has defined here, and a semicolon after each command represents the fact that the output of the command is being stored and is at present not being expressed. We need to give an energy range for the plot. Like there will be a minimum energy range, there will be a maximum energy range, and the number of points, the number of experimental data we require. Like here in this case, we have chosen it to be 1000. If we don't give any choice, it automatically takes thousands as the number of data points. Then this expression is expression obtained for the case of density of states. Like here, this is the expression. Although we have written the density of states proportional to rho t, but actually the expression with all the constants and all the variables before root e is 1 by 2 pi square 2m by h cross square 3 by h can be easily obtained from the relationship between E and K. This can be done. Right. So this is the expression that has been used in the MATLAB code. See, the same expression has been used in the MATLAB code to find out the values, and then it has a plotting of the codes has been taking place. For plot also you need to know certain commands, like if I say plot E and G, the first one will be taken as X, the next one will be taken as Y. We can give colors to the line, like here B dash stands for blue, it can be red, green, yellow, cyan, etc. And lastly, we need to give how thick my experimental, the plot will be. Like here, if it is 2, then it is reasonable thickness. If you want higher or lower, higher parameters can be set. And then we need to give the X and Y labels. And lastly, we need to give the title of the plot. Okay. Right. Now, there is one single aspect that I would like to tell you. Whenever a MATLAB command consists of a dot at its end, it represents that it is being considered for a series of values. It's not for a particular value. So this dot represents that one. Now, we have done the three-dimensional free electron in three-dimensional state, three-dimensional particle in the box model. And the degree of freedom there is 3, because there has been no confinement taking place in a particle in a box model. And as we have found that the density of states varies in terms of a parabolically with energy. So this has been expressed here. So these 3 lines represent the 3 degrees of freedom, and there is no confinement at this point of time. And we go to the next regime of starting to confine one dimension one by one. So let's start with, if we have confined, say, this dimension, the one which is being represented by this arrow. A confinement in this dimension will cause a 2-dimensional nanomaterial, because although the confinement has been done in other dimensions, are still not confined. So this is falls in the category of a hybrid nanomaterial, where the confinement is not exactly hybrid, a 1-dimensional or 2-dimensional nanomaterial. We call it as thin film at the plate or the film structure. The next case is when we are confined in another dimension. So here the degree of confinement is being reduced. So in this case it was 3 at the bulk, then it went to 2, and now at this point it has gone to 1. So it means that the electron can only travel along the length. Okay. There is no other option to drift away. And lastly, if we confine all the dimensions, we form a quantum dot. Now the density of states is different for each of these cases. For the 2-dimensional confinement, the density of states is usually a constant value, and for a 1-dimensional or material with 2-dimensional confinement, it again approaches the parabolic value, but in an opposite direction. So it's root E here, and in the case of probabilistic, it is root or 1 by root E. Root E, right? So this gives it the slope like this. And lastly, if it is confined in all the 3 directions, then we actually form a quantum dot, which follows the delta function. So again, in the MATLAB codes, if we are asked to write a MATLAB code for this 2-dimension and 1-dimensional confinement, the simple minor adjustments that we need to do is we need to first mention that it is what type of confinement is this. Then we will simply use the values available for this confinement, the DOS values. DOS values was found to be 1 by square root of E if it is a one-dimensional confinement, and if it is a two-dimensional confinement, then it is a constant value. So this is how the plots are attained. This is for a three-dimensional, that means no confinement has taken place, so it is usually following this E versus K plot, where E is equal to H cross square, A square by 2m. And here the confinement, the plot corresponding to the three different confinements are shown. So you can see that this is the starting 3D electronic materials. Then we move to films and plates. It becomes 2D electronic materials, where the density of states is proportional to a constant. And then again we have the 3D materials, where the density of states follows the inverse property as found in the 3D materials. And so this is the 3D one has been where no confinement has taken place, has been shown separately, and it is showing a parabolic path, and the E is related to x by this relationship, so it forms a parabola.